anyone can analyze networks. What's a rumpus? I'm Asaf Shapira and this is NETfrix, the network science podcast. In a recent post in a data analysis group on Facebook, someone posed the following problem. He wanted to know which product of his company is usually bought with which product. A brief inquiry revealed that he doesn't program, but far worse than that, he wasn't aware of episode 8 on NETfrix in which this exact issue was discussed. So I was able to solve at least one of his problems. But what about programming? Can only programmers analyze networks? In this context, I'm reminded of Pixar's movie, Ratatouille. In this movie, Remy, the rat, becomes a chef, and so conveys the message that anyone can cook. However, this message downplays some of the plot, like the fact that Remy was almost killed several times, forced to steal food, and had to deal with hostility from family and friends. So, unlike being a chef, network analysis doesn't usually involve near-death experiences, and for those who want to try it, this episode aims to make life much easier. So, what's the secret? In this episode, we will talk about and survey accessible network analysis software, meaning that you don't need to program, nor do you need a special database. An Excel sheet will do the job just fine. And last but not least, the software featured here are free. With their help, we can display our data as a network and analyze it. Although programmers can use network analysis packages such as NetworkX for Python or iGraph for R, still I guess at least some of them would prefer to work with a designated software, either to save some effort or to better rely on best practice, or both. Speaking of, in this episode, we'll talk a bit about best practice in network analysis and get to know some advanced concepts in the networks field, things like matrices and higher order networks or hypergraphs. And this is why I'm giving the heads up early on. For the purpose of this episode, I assume that the basic concepts of network analysis, such as centrality measures, community detection, and so on, are already familiar to the listeners. For those who are first-timers, I recommend to start with episode 2. For those who just need a light warm-up, I recommend episodes 4 and 5 on the subject of centrality measures and community detection, respectively. During my research for the survey, I found at least dozens of network analysis software, but only a dozen of them met all the criteria. The first, that they don't require programming and can run on a PC with Windows. The second, that they can upload Excel files. And last but not least, that they are absolutely free. No trial period is permitted. Some may have a premium version, but we won't expand on its features. While reviewing the different software, I've noticed an interesting phenomenon. Though about half of them were poorly maintained for years, it seemed as though from the moment I started the survey, many of them released a new version or plan a significant upgrade this year. Maybe I just experienced the Bader-Meinhof effect, but perhaps it's something else. Could it be that all the lockdowns we endured these last 2 years resulted with a baby boom of network analysis software upgrades? Was it just a way to pass the time, or is there something else at play? The answer might be found in Barabashi's reply to a question I presented to him on the 2021 Networks Conference. Albert Laszlo Barabashi is considered to be one of the founding fathers of network science, and I asked him how come the general public is familiar with concepts like machine learning and AI, but the vast majority never heard of network science. That's what he had to say.
And what I want to actually change a little bit, pivot on the question that we got from Asaf Shapira. And I know we're not in the questions part, but I thought it's really a very good question for us, because it's the question is like the concept of machine learning and AI has gotten so much attention. And compared to that, networks are not so much on people's mind. And what could we do as a community to really get more acknowledgement of the many awesome things that network scientists have done in general? I should say that we are in a historical moment, because I think COVID has raised huge awareness of network thinking. There are many, many examples. The great work that many network scientists have done on predicting the epidemics and developing better models of epidemic processes, all the way to contact tracing, which is fundamentally a social network problem, right? That is well within the social network community's realm. And many social network experts actually very deeply engaged, or that we were focused on finding drugs using subcellular networks, biological networks to identify new drugs for COVID patients. And I often joke that this is the moment of networks because people were discussing quantities like reproduction rate, like number of contacts people have, like contact tracing. They were using terms, the population at large and the press, that previously you would only hear at the network science conference. So I think in that sense, the perception of the importance of networks have changed very positively. The question I would kind of ask, in kind of paraphrasing Asaf Shapira's question, how can we educate the world at large of the importance of networks?
I guess it's too early to say, but perhaps Barabashi was right, and COVID 19 did usher a growing awareness to network science, which might in turn resulted in the upgrading of network analysis software. Yet another sign to the growing interest in networks is that for the first time, we have Nobel laureates from the field of complex systems. And as we all know, networks are a big part of this field, so respect. So, on this optimistic tone, let's get down to business. We'll review the basics of each software, what sets it apart, and what are its pros and cons, keeping in mind especially those which are just starting out in the field. Along the way, we will learn a little about the analysis process and advanced concepts in network science. Our review process will try to run parallel to the actual analysis process. So, first of all, we'll start by talking about installing the software and uploading the data. The installation is mostly straightforward, or in the case of browser based software, not even required. Some of the network analysis software are Java based and therefore may require Java installation as well. It's not complicated, just go to Google, search for download Java, and download. But uploading our data can be a little trickier. The usual practice for uploading data to network analysis software is to upload two separate files, in our case, Excel or CSV files, an edges file or table, and a nodes file. The edges table is mandatory and will usually contain two columns, source and target. This should be enough for most software. Sometimes you might wish to add a weight column, that is, the count of edges or links between the nodes, but most of the time it's not required and the software will do the edges count by its own. Most software will also allow you to add more columns that contain further information about the edges, such as the type of relationship, a timestamp, and so on. The latter is necessary when doing dynamic network analysis, which is sadly not a common feature in network analysis software. In regard to the nodes table, it's optional and is mainly used in cases when we wish to show the node's attributes in our analysis. This table will usually require two columns, which will include in its header an ID column and a label column. The ID column serves as the pointer for the software to identify the relevant node in the edges table. That's why the ID of a node should match exactly to the node as it appears in the edges table. The second column will include the description of the node. Again, in many cases, it would be possible to add more columns with a variety of descriptions and information about the node. If you just wish to test drive the software, most of them come with the sample networks that can be loaded directly from the software. It usually contains classic datasets from the field of social network analysis, some of which we have already touched on, for example, the Zachary's Karate Club network. Another quick way to test the software is by generating a graph, which is a common feature in most software. By choosing some parameters, the software can create a graph for you. This feature is mainly used to test graph attributes in the field of graph theory, but since this episode is dedicated to real-world networks, meaning SNA and network science rather than theoretical graphs, we will hardly address this feature. But by far, the coolest feature is that some software allow data to be streamed from an external source, or API, most commonly Twitter, so you can harvest it directly via the software. In some, you'll need an API key, but some software only requires a Twitter account to enable this feature. Now that we have the data, the question is how much data can the software handle? I guess most of us would not launch our network analysis career by analyzing networks in the magnitude of millions of nodes, but a few thousands, why not? That's why it's important to note that not every software can handle such a quantity and keep pace. Most of the software were designed for small networks with only a few that can handle networks larger than 10,000 nodes. But this benchmark can vary by our willingness to wait for the results. For the purpose of this survey, I tested each software on a standard laptop and ran with it a network with tens of nodes, a network with thousands of nodes, and a network with tens of thousands of nodes. If the software took more than 2 minutes to respond, I gave it the mercy blow and pulled the plug on the poor thing. Now that everything is ready, it's analysis time. So, how intuitive is the analysis on each software? Because intuitiveness is a bit subjective, I use the Israeli benchmark. Never read the manual. If it works, it's intuitive, and if not, we'll bend and crank it until it works or breaks. On some software, I had to admit defeat early on because they required a unique format to upload the data that doesn't conform to the standard source target format. In that case, you sadly have to check the README file. Once we know what's what, we can continue our survey by checking what algorithms and visualizations the software provides, and does it allow for an iterative process between these two. We'll start with the algorithms, and they split to basic and advanced. When I say basic algorithms, I mean the centrality measures, degree betweenness, and my close friend closeness, and also basic network metrics, for example, calculating the network's density or its diameter. For the purpose of the survey, community detection isn't considered a basic algorithm, but I highly recommend to apply it. There's a wide and eclectic variety of community detection algorithms, but as I see it, a software that doesn't have the Louvain algorithm, well, it says a lot about it. Full disclosure. First, while talking with French speakers, they insisted on pronouncing it Louvain and not Louvain for some obscure reason. Second is that I'm a sucker for Louvain. It's a great algorithm. So, now that we covered the basics, let's move on to talk about more advanced techniques, and we'll start with the subject we haven't covered yet in this podcast, and by that I point to the elephant in the room, the matrix. A psychopath once said that there is more than one way to skin a cat. This is also true of networks. There is more than one way to store our data as a network. So far, we have mentioned two techniques: the visual method, that is simply drawing the networks as nodes and edges, and the second is the edges list, which is the source target table we mentioned earlier. What we haven't mentioned is the adjacency matrix, which can be used to show which node is adjacent to which node. This matrix is basically a table with as many rows and columns as the number of nodes in the network. That is, a network with 10 nodes will be displayed as a table with 10 rows and 10 columns, and the nodes will be assigned as the headers of these rows and columns. In each intersection between two nodes, the cell will contain a numeric value. If there's no link or edge between the nodes, it will be 0, considered as false. If there is a connection, it will be 1, considered as true. In a weighted matrix, the value will be the count of edges between the two nodes, or in other words, the weight of the relationship. The diagonal of the table, meaning the cells where the column and row of the same node intersect, will show the self-loops in the network. Usually it will be 0, but there are some networks where self-loops can be found. For example, in an email network, I can send an email to myself. In practice, these cells are often ignored. The whole idea might sound a bit complicated, and the first thing that pops to mind is, why do it? Moreover, it also sounds very wasteful in terms of data storage. Think, for example, of a network with 1,000 nodes. It means we need to keep a table with 1,000,000 cells that most likely the vast majority of them will be empty or contain 0 values. Why is that? Because, as you might remember, networks' edges form a long tail distribution, meaning most of the nodes will have only a few edges or links. So, why should we use matrices for these sparse networks? One reason is that although an adjacency matrix is wasteful in space, it can be economical in running time. Thanks to the matrix, all the nodes' neighbors appear in each row or column, and so we can quickly check which nodes are connected to which nodes. In order to optimize the two methods and save both space and time, there is another method that is a hybrid of the two, and it is called an adjacency list. The list contains two columns. On the first one are all the nodes, and on the other column, all of the node's neighbors. That is, if we have a network where the node A is linked to nodes B and C, node A will be placed on the first cell of the first column, and on the same row in the second column, there will be nodes B and C, meaning all the nodes A is linked to. On the second row of the first column, we'll have node B, and on the cell in the column next to it, we'll have node A. C is missing because C isn't linked to B, just to A. This way, we don't waste space on links that don't exist, and at the same time, we can quickly find neighboring nodes. For those in computer science, optimizing efficiency in data storage and retrieval is important. That sounds cool, but again, as a user, who cares? A simple source target table should be enough because it's the software that's doing all the heavy lifting. That's true, but there are some algorithms that rely on the matrix format as an input, because they involve matrix multiplication and other sorts of math voodoo. We won't get into it now and save something for the next episode, but for the time being, let's just give a simple use case for it, such as finding similarity between nodes. When we compare two nodes in terms of their role and location in the network, we are required to compare their neighbors as well. And the best way to find neighbors is by using a matrix. Finding a large percentage of common neighbors between these nodes will give these nodes a high similarity score. In a social network, this could mean that these nodes share many mutual friends, and if there's no link between them, the application might suggest one. Perhaps the most common application these days for such use cases is in the field of machine learning on graphs called GNN or Graph Neural Network, which is a subject I might cover someday on this podcast. Matrices open a door to many applications in the network field, but contrary to what I usually say about networks, they're not always simple to grasp, and even computers have a hard time dealing with them, resulting in longer running time. Fortunately, and I hope I'm not offending anyone, most of the time we won't need it. Moreover, the results we'll get from some of these algorithms won't be necessarily much better than simpler and often more up to date algorithms. Now that all the computer science fanatics have clicked pause and unsubscribed, I can secretly tell you that some software can perform the conversion of an edges list to a matrix by themselves, with no action needed from the user. But when we'll move to the next issue at hand, visualizations, we'll might need to rethink our view of matrices. Now that we have our data and we know which algorithms we need to apply, let's talk about the visualization features. Almost all software will have some editing features which can be applied to the nodes and edges, like sizing them according to their centrality, changing their colors, and so on. But the more advanced features we'll address is the layout options of the network. The bigger the network, chances are that the nodes and edges will overlap, and sure enough, they will get to a state which is known in the professional literature as the giant hairball effect. This messy ball of yarn makes the network incomprehensible. That's where the various network layout configurations kick in. They use algorithms that aim to maximize certain features of the network according to the user's visualization need. For example, a layout algorithm can maximize on the proximity of nodes to each other, meaning pin nodes connected to each other and keep other nodes away from them. Other algorithms can maximize on the desired layout style. For example, display all the nodes in a circle or in a hierarchical configuration, or even allow the nodes to be displayed according to their geographical location. For example, by embedding them on a map. On a personal note, my go-to layout is the Force Atlas 2 developed by Mathieu Jacomy, which is great for large networks. It usually does a great job of highlighting the network's communities, making the network more readable in the visual sense. Though I can deeply relate to those who have been captivated by a particular visualization or layout because of its aesthetic beauty, looks can be deceiving. That's why there's best practice literature on how to visualize networks. In the episode transcript, I reference to none other than Mathieu Jacomy, which runs a blog about it, and, spoiler alert, he will also be our guest toward the end of the episode. Speaking of visualizations, I would like to take the opportunity to recommend Christian Miles' newsletter called Source Target, which deals, among other things, in networks visualization. In this newsletter, I found a link to a paper who claimed that sometimes networks are better represented visually when they are in a matrix form rather than in a node edge form. Their main claim in the paper was that no matter how dense the network is, matrices don't suffer from overlapping nodes and edges. And, well, that's a good argument. But since no software I've surveyed lets you play with the matrix visualization mode, we'll keep this one theoretical for now. So, now that we can analyze our network by using algorithm and visual aids, we need a software that can iterate between these two. To gain insights on our network, we'll usually need to go back and forth between the algorithm's results and the visualization. The process might also involve some filtering or even exporting the data to continue our research on another software. Iteration is an important feature, especially for beginners, but also whenever we do some exploring on our network for the first time. Sadly, not all network analysis software enable this workflow. And now at last, we can begin our software survey. And when I say software, I actually mean Gephi. One reason for it is that there's lots of software to cover, so we can't cover all of them in one episode. The rest will be covered in the next episode. Also, to try and keep it light, the more detailed content can be found in the show notes. But there's also a second reason for it. I'm a sucker for Gephi. When it first came out in 2009, Gephi had about 10,000 downloads, but 7 years later, it had crossed the 2 million, and by unofficial polls, it seems that even today it's probably the most popular network analysis software. As I tell my kids, this is not a competition, but Gephi wins. The founding father of Gephi is Mathieu Jacomy, whom I mentioned earlier. On the interview, he'll reveal to us some new features, and if you are a Java developer, he'll make you an offer you can't refuse. Gephi is a Java based software that, at least for now, requires installation of both the software and Java's latest version. Gephi also comes with a lot of plugins, that is, other features that also need to be installed, and the good news is that lots of them are quite useful. We'll start with Gephi's most renowned features, visualization and scale. As for the visualization, there's almost nothing you can do with it. That's why a lot of network posters you'll find on the web were made on Gephi. It's also one of the few software that allows you to run Jacomy's layout algorithm for Atlas 2. As for scale, Gephi is one of the best, and can pretty well handle networks with tens of thousands of nodes and edges. According to some brochures, Gephi can handle hundreds of thousands of nodes and edges. This might be true, but it doesn't pass the 2 minutes benchmark I mentioned early on, and I bet Gephi would crash most of the times. It sounds bad, but keep in mind there's only one software out there that can outperform Gephi in that regard, and we'll cover it on the next episode. As for intuitiveness, I'm not so objective because I've been working on Gephi for a long time and even wrote a basic guide to it in Hebrew for Israeli research teams during COVID 19. Is COVID 19 still an issue these days? I guess the obvious conclusion is that if it had been intuitive, there would have been no need for a manual. So, for those who wish to take their first steps in the field, Gephi will require some getting used to. Why? Because sometimes even basic functions are hidden under non-intuitive headers. For example, in Gephi, if you want to analyze key metrics like closeness or betweenness, you need to click on the function calculate the network's diameter. Only then do you realize that it analyzes the other centrality measures as well. Although computationally this can make sense, it's a pity to make such a basic operation into a kind of an Easter egg for the user. Speaking of centrality measures and basic algorithms, Gephi, of course, has you completely covered, Louvain included. And to the best of my knowledge, it's also the only network analysis software that has the Leiden algorithm, which is considered the improved Louvain. But again, to apply it, you need to install the relevant plugin. Thanks to its 100 or so plugins, Gephi also enjoys a large variety of advanced algorithms and features. One of them, which is not so common in network analysis software, is the ability to play a dynamic network. Given that the network edges or nodes have a time label, Gephi allows you to play the network and so watch it change. Needless to say, it's a nice feature for small networks, but on large networks, we'll probably lose our hands and feet if we try to figure out what's going on by visuals alone. Another nice feature in Gephi is the ability to perform projection, a feature which we mentioned in a previous episode, and it does so quite comfortably and intuitively. Again, you'll need to install the relevant plugin. Besides its features, Gephi is a great tool to explore networks because it allows the user to easily iterate between analysis states. Once you open Gephi, you can move between its three main tabs. The Overview tab, which is where the analysis process takes place, and it has a visualization window and the analysis toolbox. The second tab is the Data Laboratory, which presents the tables of the nodes and edges. And finally, there's the Preview tab, which is where you can polish the visualization to fit your PowerPoint needs. The Overview tab keeps the relevant analysis toolboxes close at hand, plus a user can toggle comfortably between the tabs. For example, you can highlight a node on one tab and view it on another. A major drawback, though, and it may sound a bit silly, but I can see how it can be irritating to some, is that it takes some mouse skills to pan and zoom the network when you're using the Overview tab's visual interface. When this happens, I advocate patience, and remember, it's all in the wrist. So, in conclusion, what are the pros and cons of Gephi? A significant advantage of Gephi is that it's a one-stop shop. You can perform an end-to-end analysis of even large networks and not feel anything is missing. The fact that it is expected to undergo a significant facelift and include new features makes it score even more points. I don't want to steal Mathieu Jacomy's thunder, but I got to mention one of the new planned features, and that is hyperedges. This is exciting news because there is currently no free software that have it. So we need to stop for a moment and explain what are hyperedges. In traditional network analysis, each edge connects two nodes. But there are real-world use cases where an edge can connect more than two nodes. Let's give an example. Suppose we have a network that consists of three nodes, A, B, and C. Let's say that A corresponded with B, B corresponded with C, and C corresponded with A. On this network, we have now three pairs of edges forming a triad or a triangular graph. A hyperedge is formed when A sends a message to node B and to node C simultaneously. In this case, the edge stands for a parallel action that simultaneously connected more than two nodes together. In order to differentiate this edge from a standard edge, it's called a hyperedge, which can be found in higher order networks. In recent years, there's been a growing interest in the concept of higher order networks as a model that can improve the resolution at which we analyze networks. I hate to say it, but Gephi also has some drawbacks, and I'll begin with a story. When I was little, we would sometimes go to the mall to a big restaurant, which I recall had many food stands. Each food stand offered a different cuisine, which is a fancy word for fast food. There was hamburger stand, pizza, Chinese, Indian, and so on. And even though it wasn't the most delicious meal, the mere ability to choose from a wide variety really impressed me as a child. Needless to say, this restaurant has been closed for many years now, probably because of health issues, but why am I telling this? It's not my intention to imply that Gephi gives a mediocre solution to a wide range of issues. It's just that when you disperse your efforts, it comes at a price. In the case of the aforementioned restaurant, it meant that all the food there had a greenish hue, and to this day I can't explain its source. In the case of Gephi, the tool is a non-intuitive UX, user experience, and at least for now, a stability issue. When there are so many features, sometimes some of them get crammed into all sorts of tabs, making them hard to find. And as for the stability, sometimes when running a particular feature, Gephi crashes, probably because not all of the plugins play nicely with the rest. Clicking the Save button before each time you try a new function won't necessarily be so attractive to every user. Personally, I consider it as a bonus because it both toughens you up and serves as a contingency in the case of a sudden power outage. So, is it a bug? Is it a feature? See? This is true love. when you love in spite of the flaws and perhaps because of them. That's why on the next episode we'll compare the rest of the network analysis software to Gephi. Its wide range makes it a good benchmark for the rest. And now, to the guest of honor. Okay, so as you might have noticed, I'm a sucker for Gephi, so that's why it's a real pleasure to present today's guest. I make it a habit to retweet or post the great articles he writes about network analysis, so no wonder I found myself flirting with him on Twitter to get him on this show. And since we are discussing network analysis software, what better guest than the founder of Gephi? So, Mathieu Jacomy, what's the rumpus?
Hi there. I'm super happy to be here with you guys. So, I didn't know that expression was the rumpus, so I don't know what it is. But yeah, I'm happy to be here.
Cool. And congrats are in order. You got your PhD this year, right?
Yes, absolutely. So I'm very happy. People who hear us and want to see the PhD defense, you can see it on YouTube if you want. It's about networks, but it's from techno-anthropology. So, science about the science of networks.
Oh, we love the meta stuff. We love the meta stuff.
Good.
Cool. So we're here to talk about Gephi. How many people use it?
Okay, so we don't have an instant view of the number of people who use Gephi. So it's been downloaded something like 2 million times since the beginning. It's 10 years old. So yeah.
Wow.
And we can also count the number of papers who cite Gephi. And it's cited more than once a day.
How do you explain the Gephi's popularity?
Okay, that's a really good question. So I think that the question breaks down like that. How was it famous in the beginning? And that is a bit of a mystery because we were kind of surprised. As for why it's being used today, it's because of there is this legacy. So it's used by people in the community. The teachers are used to do that in their courses, so they will propose it to the students again and so on. So you have this kind of virtuous circle that sustains the usage of the software, also maybe because it's good. But I think that the more important question is that what did Gephi have in the beginning that other softwares didn't have? And I have to say that I built Gephi as a reaction to another piece of software that was great for the record, and it was called Guess. It was from Eitan Hadar, and it's the famous software that was used for Divided Dayblock, the paper by Lada Adamik and Natalie Glantz about the US politics in 2004. So they used that tool, and we wanted to copy what they had done. And it was great and frustrating at the same time. The issues we had with Guess, that software by Eitan Hadar, was basically that it was a lab software and not an engineering software, in the sense that it was very slow. So for instance, we thought, hey, we have all this power in the graphic cards of the PCs, and we know we can display millions of polygons because that's what any video game would do. We basically wanted to redo it in a way that would be more efficient, because we wanted to be able to interact more actively with bigger networks. We wanted to have this immediacy of an interactive software. Basically, we wanted something like Photoshop, right? But for networks. And I think that's what makes kind of the flavor of Gephi. It's especially in the beginning, it was not state of the art. It was not complete with a lot of algorithms and stuff, but it was more efficient, a little bit more scalable, more easy to use, because we wanted to do that not only for ourselves, but also for other social science researchers that were around us. We expected Gephi to be installable, right? You would double click a setup icon and it would get installed without any command line to type and so on. We wanted a graphical user interface. That's the place Gephi comes from. And I think that this is at the core the reason why people have been drawn to Gephi, because of this immediacy of the experience as a user.
Mathieu Jacomy mentioned Lada Adamik's paper, which was discussed on a previous episode about politics and networks, but just a quick reminder.
It measures the polarization of the US political life by looking at blogs. It was a time where blogs were more important than Twitter or Facebook, right? So you would see in the picture we talk about these two balls, one blue, one red, that are well disconnected, and it really makes you see, or you believe you see, this polarization. But it's worth reminding then that this picture is very special because it's so obvious that you have two components to that network. Like the network is very caricatural. It's been inspiring a lot of people, but it's worth reminding that if you do that at home, you're not going to get something as clear as nice. Most of the time, you have something that looks like a hairball to some extent, and then you have to do a lot of work to find something to say about it. So
Yeah. Okay, so back to network analysis software. That's what we're
yes,
here for.
okay.
Do you care to comment on other, let's say, competing software? Though I guess there's no competition, but still, like I don't know, Cytoscape.
I don't have much time to use other pieces of software, which I regret. I know a little bit of Cytoscape. What it seems to me is that it's a tool that does many things, which is absolutely great. It has drawbacks and advantages, but there is nothing wrong with doing a lot of different things. It can have a lot of different plugins, and it seems to be very well focused for the community of, I don't know, bioinformatics, genetics. And I think that with time, each different piece of software found their own space, which means that Gephi is not much used for biology, genetics, and it's more used for as an entry point to analyzing networks in the social sciences and humanities. Even though if you want actually to do some social network analysis, you may use other tools like UCINet. Payek is still used sometimes. Of course, I know Payek, which is our granddaddy, the granddaddy of all these network softwares. There are other more niche, smaller tools that have their specialty that emerged, and I really like that. I think that one of the discussions we could have is what different tools give you if you have specific use cases. So, for instance, GraphViz, which is basically a command line tool, will be very good if you have sophisticated things you do and that you can describe if you know the software. While, for instance, Gephi will be easier to use if you don't really know what you want or where you go, because it's more direct to your face and you can tinker with it and play. The reason why you would use one tool over another is because it solves a specific problem to you. And I think that Gephi solves a lot of the specific problems of the beginners, but other tools solve the problems of non-beginners in various ways.
Yeah, that's one thing I like about Gephi is it feels like it's a one-stop shop and can handle large networks. I wonder what your understanding of the features usage in Gephi. Do you feel there are unused features that people maybe don't know of or don't take advantage of?
Now that's a hard question because I think that one of the characteristics of Gephi is that it's a pretty curated piece of software. So there are not as many plugins as there could be as Cytoscape, for instance. And we have actually removed a number of features. That's part of the identity of Gephi. Now, of course, there are some features that people don't use. Maybe it's used. I just assume it's not. It's the ability you have to settle a node. So in the overview, where you have basically all your nodes and links as visual objects that can move and so on, you can right-click a node and click on settle. And if you do that, the node is from now on unaffected by the layout. So it's basically locked to the metaphorical surface of the screen. And so you can still pan and zoom, but it's in place. And you can do that to as many nodes as you want, and then you can unlock them and they will be affected again. And so there are many ways you can play with that. So for instance, you could filter your network in a specific way, settle the nodes that remain, then show everything, and then run a layout. So it plays with the statistics, it plays with the filters, it plays with the layout. And you can craft your own manual layout if you want. Yeah, for instance, you could pick 3 nodes that are really important to you, put them in 3 very distant places, settle them, then run the layout, and then it would stretch the whole network structure between the 3 nodes, and it would make certain things appear, right? So that's when the stretchiness of the network through the layout can become a creative tool for you to explore certain dimensions of your network. So I encourage our listeners to try the settle feature. Yeah.
Yeah, I actually used it this week. So,
Oh,
okay, so cool.
Dan, maybe it's used.
Maybe it is. Yeah, who knows? You mentioned the plugins you removed. Why? Because there were bugs, or because of?
Oh no, we didn't remove plugins. We removed features. So, for instance, one of the early features of Gephi was you could live group the nodes. It would make a graph of groups, and you could pack nodes inside a node. I don't know if I'm clear.
Yeah, aggregate a node. Yeah.
Exactly. And then the graph coarsening could be made in that form, and it was poorly used, and it brought some side effects that were complicated. So that's why we removed it. This is a kind of a constant discussion. So for instance, we've early made the choice of not having parallel edges, but we are coming back to now, we think we are going to implement parallel edges.
I tried to leverage the interview to get the aggregated nodes feature back on Gephi because I find it very useful when analyzing a large network. One can use it, for example, to aggregate the nodes to a community graph, and so you can get a clearer view of the network and the role of each community in it, which we discussed on episode 5 about communities in networks. Jacomy didn't promise anything, but time will tell. I also asked him about the lack of matrix-based algorithms in Gephi, such as node similarity or Markov clustering.
There is a rationale for that. If you want to get efficiency in your algorithms, you have to not think in terms of matrix when you do the implementation. It's much more efficient to manage a list of nodes and a list of edges. This is also an engineering problem because all Gephi is thought on this paradigm lists. So we do not even have an object matrix in the source code that we could deal with. While I think other softwares, they do have that, and they would use sophisticated code libraries that do the optimization of sparse matrices computations for them. One of the reasons we do not go that route is that we want to also limit the dependencies of Gephi. It's much more integrations of other components, and then you add dependencies. And also because, let's say it this way, we are not great at math. Like we do math like non-mathematicians. And I'm one of the guys who has actually done the math of certain things and implemented or published algorithms like for Atlas 2. But although I do like math and I had some amount of training about it, I'm not into the community enough that I have a good vision of what the good code libraries are and so on. At the end of the day, the goal is to maintain scalability. So as soon as you deal with matrices, you are at risk of having less scalability.
I see. And for everyone who doesn't know, the Force Atlas 2 is the best layout algorithm. So
I'm glad you like it.
Use it all the time.
Good.
Okay. And we talked a bit about it, but what Gephi is missing, you mentioned the parallel edges or hyper edges.
That's an easy question because we have requests for new stuff all the time, basically. So the biggest complaint is that it has no undo button. I really like the activity log, the series of the last tasks you have done that provides you an ability to go back into the list. You have that in OpenRefine, for instance. You have that in Adobe products like Photoshop and so on. I think this would be great for Gephi, and it's also a way to think of the undo button. We missed curved edges in the overview. We have that when we export a network, like as an image, like a PDF, but we do not have that in the live interactive part of Gephi that we call the overview. We would like to have a real application that doesn't rely on Java, for instance, so that people do not have to separately install Java. And then, of course, reaching the state-of-the-art modularity clustering, layers, statistics, and so on. This is an endless endeavor. To some extent, the tool maker, so in that case, it might be me or our lead dev, Eduardo, or Mathieu Bastien, our original lead dev. Like we would be our own guinea pig, our own test user. Like we would develop Gephi for ourselves and make the calls of what's right in the UI and so on. It's good to keep the integrity of the software, but at some point, if you can afford it, and I mean, if you have time to code and improve it, you have to reach for what other people do. We are often surprised by the creativity of Gephi users. They would use Gephi in ways that we didn't expect. There are so many interesting people who are using Gephi as a way to introduce their students, for instance, to network science. They have their own specific cases in mind, and they have ideas of needs that I don't know.
I think that's a good time to plug in the Gephi retreat.
Oh yes, so we have developed Gephi spasm by spasm with sometimes years where we didn't really push much. That's because any project like that is a burden as well as it's a boon too. No one is paying for Gephi, it's free. And so we have to find our own free time. We would like to get some fundings, but we are getting there. So our big plan is to, first of all, make the code base more easily maintainable and appropriable by new developers, because we want to find new developers for Gephi. So if you hear us and you want to contribute to Gephi, just contact me. You will find my coordinates, because we are looking for developers in Java, of course, because all of Gephi is in Java. We want to grow a team around Gephi's core. And we have a sustainability retreat, which is hosted in Copenhagen at the end of November, where we will have some old people of the project and some new people. So we will have our current lead developer, Eduardo, and our ancient lead developer, Mathieu Bastien. Mathieu is basically the father of all the software aspects of Gephi. He took my prototype and make it something that actually works. He's the person who knows the best the code base of Gephi, while I'm more kind of the designer / algorithm maker. And then we have new participants, including, for instance, Thiago Peixoto, who is a world-class expert on community detection. And he also has developed his own library of code called Graph Tools, that is kind of more of a command line tool than a graphic user interface tool. And we hope to be able to do that every year. And starting from next year, we will try to raise some funds to organize this coding retreat.
I had to interrupt to say that I don't know if this episode would publish on time for the retreat, but Jacomy reassured me.
We do seek developers for after the coding retreat. So if you hear that years in the future, so in 2020, 23, 24, keep reaching for us.
I've noticed that in the last few months, many software have now new versions, like Cytoscape just released one, Visionnet, which hasn't released one in, I think, 3 years. You're getting your retreat. Maybe it's COVID-19 that kicked in. People are staying at home and they have nothing to do. There's something in the air for a network analysis software, it seems.
But I think that one thing we could tie that to is the movement of open science and open source software. And here in Europe, with other researchers, we organize a track at the FOSDEM, which is the Free and Open Source Software meeting. Sorry. So the FOSDEM is this big conference with many tracks that are called dev rooms, where everyone comes to talk about open source. That's where we met, for instance, Antonin Delpech, who is maintaining OpenRefine, and he will be here to help us also at the Gephi sustainability retreat. Academia is traditionally hostile to the work of programming. I was really surprised that some of them told us that in some fields, if you develop a tool, you have to hide it because it could be detrimental to your career. As if creating a tool is shameful, you know? But that's really how it is. But the situation is changing, because you have, for instance, the Journal of Open Source Software. You have a number of places where you can valorize your production of open source software within the academia. You can get a DOI to make the version of your software citable. For instance, just with Jupyter notebooks, right, is the fact that it's still credited to the original authors. People are still citing the original paper, but it's been 10 years now, and the contributors are completely different now. So there is a need to be able to cite different versions of the software, so that you can get credit if you spend your time as a researcher to contribute to a tool. You can get citations, because in the academia, the magic coins that fuel your funding and your career are these damn citations. And obtaining these citations is sometimes complicated. So it gives more incentives, maybe now, to develop these tools that contribute to open science. And maybe that helps this project. I hope so.
Cool. So thank you very much.
Well, thank you for having me.
So thanks to Mathieu Jacomy. Since at the end of the day, this is only a podcast, which is a non-trivial format to survey software, I highly recommend the transcript blog, whose link is in the episode description. Wish to expand the network science and the SNA community? The more you rate this podcast, the more people will be exposed to it. Rate the podcast on Apple Podcasts and or write a review. Creative reviews will be read in the following episodes. For those of you who are iOS challenged, tag NETfrix in posts on Facebook, Twitter, Instagram, or LinkedIn. Again, creative posts will be read in the following episodes. The music is courtesy of Compile Band. Check them out. See you in the next episode of NETfrix.
many users and from different places. Are you here, my cat? My cat is protesting.
Another guest.
Yeah.
Okay.
Yeah, she doesn't like the cables, so she was stuck in the cable of my headphones. Now she's gonna be a little bit more quiet.